Hello, this is Mr. Huff, and I want to talk about orbital mechanics, some of the math that goes behind it. So this will be a series of short videos. So if you need to know more, you can go to Activity 3.2.6 Orbital Mechanics Physics, and there's a presentation here from AGI that has some information. They do a pretty good job of showing how one of the formulas is derived, but I thought it would be more efficient just to give you a couple of examples. So let's look at the formulas from your formula sheet in my PLTW. The eccentricity and the orbital period I'm not going to worry so much about right now. I have a previous video where I talked about how this formula, really the important thing to understand is that the period is proportional to the semi-major axis divided by the mass of the central object. So one of the things I want to focus on is this law right here. This is force is equal to the universal gravity constant times the mass of the larger object times the mass of the smaller object divided by the radius squared. This is Isaac Newton's law of universal gravitation, and his ideas were built upon both the ideas of Galileo, who studied gravity, and Johannes Kepler, who studied planetary orbits. It was his pursuit of trying to understand how orbits work and how the solar system works and how those forces interact that led him to invent calculus, because algebra just wasn't getting it done. So if you look at this, one of the things I need to point out, anytime you see this radius, that is talking about the distance between the centers. So from the center of one object to the center of the next. So in a lot of the orbital mechanics problems, we're going to be having to, it'll say something like, it's so many kilometers above the surface of the Earth. You need to take that distance plus the radius of the Earth to make sure you understand that. So I might throw a couple of these at you and we'll see how it goes. The next set of formulas, it's all about energy and orbital mechanics there. So we have kinetic energy, which is something that's probably familiar to you. We also have potential energy. The letter U is used to represent gravitational potential energy. Normally, you will see this as mass times gravity times height, but in this case, we're talking about distances that are far, far, far from Earth, so this formula becomes much more important. And again, radius is talking about from center to center. A couple of things I need to point out about the constants here. The universal gravity constant is 6.67 times 10 to the negative 11th, and it's meters cubed over kilograms times seconds squared. This is a constant that makes the formula work. So if you don't have this constant, this formula does not give you the correct answer. So that's what makes it work. I want to point out also that I'm going to use E notation, so 6.67 times 10 to the negative 11th is the same as 6.67 E negative 11. So I'm going to use this E to represent times 10 to the whatever. Another thing I don't like what they've done here, the radius of the Earth is 6.378 times 10 to the third. Go ahead and make that times 10 to the sixth so that it's meters, because everything has to be in the same units. All right, and I think that's enough about formulas, so I'll stop there.